So we start with input, okay, input side. And consider like this. So I told you that I have magnified the top portion. So all other, because since we are doing manual calculation, it's not possible to do for all the 8 weights. Okay, it's a time consuming process, and also it's a waste of time. Once you understood the logic for one weight over here, okay, one weight over here, what we consider this is W5, right? Similarly, one weight over here, what we have considered this is W1. If you understood the logic for W5, same thing applicable for 6, 7, and 8. Whatever you understood for W1 is applicable to 2, 3, and 4. So we'll say this is your hidden layer, right? The hidden layer output, let us call this hidden layer output, we call this is a small h. And the input we represented as x. And how do we represent the output as? We represent output as OUT out. What is the expression for y cap? We'll write the expression for y cap. The predicted output is so the f of net that happens at the output side. Similarly, we calculate another net value at the hidden side. So to differentiate this, we are going to call the net value at this hidden portion. We are going to call that as a net suffix h. Similarly, the net value happens over here as net suffix o. And again, what is net suffix h? What is net value? Effectively, I'm going to write this net h is nothing but, since for you only W1 is visible for you, but you know the full architecture which is available in the PowerPoint. So basically this is x1, right? How do we write net h? X1 times W1 plus second input is connected to this node via W2. So x2 times W2, which is not visible here, plus, and I'm going to call, there is a bias over here, right? So we'll call this is a W bias at the hidden. Okay. Similarly, shall we write what is the net at the output side? How do we write the net at the output side? Since we have 2 neurons in the original architecture, let us call this is a H1 and H2. How do you write the expression? H1 times W5 plus H2 times W6, which is not visible. For simplicity, I have drawn only the upper track, plus W bias at the output side, WBO. So at every hidden layer also we apply f of net to get h1, and in the output side also we apply what is nothing but your out expression is nothing but f of net o. What is f of net o? You are applying sigmoidal activation function, which is 1 divided by 1 plus e to the power minus of net o. So this is the expression. Similarly, how do we obtain h1? H1, we are obtaining h1 as a function of f of net h, which is nothing but 1 divided by 1 plus e to the power minus of net h. These are the fundamental expression before we do the calculations. First of all, are you comfortable with these workflow, the parameters? And if you have any questions, feel free to ask me. Whatever the terminologies I have used and the notations I have used to represent x1, w1, net h, and output at the hidden node, we call this is a h1, and that goes via w5. Not only h1 goes with w5, h2 also comes with w6 along with the bias. Let me call the bias weight as w suffix bo. Similarly, the bias at the hidden node I call w suffix b at the hidden. This is w suffix b at the out. So at every stage we are applying the activation. Is this workflow? If you have any query, feel free to ask me, Chaitanya. Are you comfortable with these parameters, definitions and all? Shall we go ahead? So next step is we need to define the error function. How do we define the error function? We defined error function as, let me write over here. Error is nothing but. In the previous session, I have given the reason for why the introduction of 1/2 scale factor. Because when you derivate this power 2 will come in front, so that this 2 and 2 will get cancelled, so that in my gradient term, I don't have any scaling factor attached in front. For that, only for that mathematical convenience, no other reason. So this is a squared error. So you can call this sometimes, if you sum over multiple nodes at the output, you can call it as a sum square error. So first we'll start our calculation by considering this weight. Okay, this is calculating, this is very straightforward, but calculating the gradient for W1 is a bit tricky. It's a two-step process. That is the only difference you should understand here. So first step, I'm going to calculate the gradient dou E by dou W5. What is the, this is the mathematical represent, but what is the logical meaning of this? What is the logical meaning of this? This, what I'm going to calculate something, okay, so I'm going to get some number. What that number tells, what is the magnitude of that number tells. Hey, this much magnitude, you need to adjust the W5. That is what the meaning of this gradient. Why I need to adjust? Hey, you have to adjust this much magnitude, whatever the value I'm going to provide, that much magnitude you're supposed to adjust. What is the formula? The formula of W5 new equivalent to W5 old or initialized value. Learning rate eta times this value I should substitute dou E by dou W5. Okay, into input. What is the input? It is coming from H1. So when you calculate the formula itself give you this value also. Okay, the formula itself gives this value also. So we are going to call this overall term as error gradient at the output side, delta O. Okay, so this is going to tell, hey, this much you need to adjust so that you can reduce the error. You can minimize the error in the descending direction. That is the meaning of this. Okay, now let us see how we are computing this. We are going to calculate this. So we are applying the chain rule, okay, so that we break down this calculation into three components. What is our intention? How WFI impact the error, right? The change in WFI impact the error. Try to understand the logical meaning of this expression. I'm trying to convey the logical meaning of this expression. In order to calculate how WFI affects error, we are calculating that into three components. What is the immediate term WFI is get impacted with? First, we are going to see first how W5 impacts the net value, isn't it? Because W5 is responsible to produce the net value. Then only net value is responsible to produce the output. Then your output Y cap is responsible for to produce the required error, right? So we are breaking into three components. So to get that three component, what you are going to do? We are multiply and divide by derivative of out. If you multiply and divide by derivative of out, this is cancelled and still dou E by dou W5 remains valid mathematically. Similarly, again multiply and divide by dou net at the output. So what is the meaning of this? We are break down into three components. First, how W5 impacts. W5 is directly impacting net at O, right? The meaning of this term is how W5 impacts net value at the output. What is the meaning of this term? How net O impacts net O is impacting what? F of net O you get out, right? Impacts out at output at the output layer. That is why I'm calling this as out at O. But here the out at hidden is H1, right? And finally, who is this guy? How out at O impacts. Finally, what is out at O? Y cap is nothing but your output at O. Okay. Out at O, also you can write this as your predicted output cap. How out at O impacts your final error. Impact your error. So both are mathematically equivalent. You, instead of telling that, directly calculating how W5 impacts the error, instead of communicating how W5 impacts the error, you are trying to communicate into three components. What do you say? First you say how W5 impact this guy and how net O impact this guy and how out O impact this guy. You are taking an indirect route. Why we are taking indirect route? Because it is easy to compute. We have break down one complex calculation into three chunks of a smaller calculations. So it is we can easily break down. Now we are going to compute each component. Why we are doing like this? So that you can apply the same strategy for this guy also. And how the strategy is going to work for this guy? Okay, once we simplify, once we come to this place, you will appreciate it. Even though I have told in the previous session as a quick recall, okay, to re-emphasize the concept, what you have discussed in the session 2, okay, I'm going to re-emphasize again. Okay, now we will work out these calculations. Three calculations are very simple and straightforward. We have extensively done this part in the previous session. Already we have the expression for the net O, right? It's the expression for the net O. When you derivate this expression net O with respect to W5, these two terms are constant, become 0. What is the output you get? If you derivate this with respect to W5, you will get only H1, right? If you derivate out, this is the out function with respect to net. In the previous session, we have used U by V method and we have got the derivative of this f of net. We called as f dash of net. That f dash of net you can shortly refer as y cap into 1 minus y cap. Okay, this is nothing but y cap into 1 minus y cap. How we arrived this, please refer, if you forgot this, please refer to the session 2 recording. We have done u by v calculation, derivative of u by v calculation, and final expression we write in the form of y cap into 1 minus y cap. Finally, we come to this portion. This is the error function, right? The error function, if you derivate with respect to out, this y cap is nothing but out. Okay, out. You see some literature, you notice this as a out into 1 minus out. Both are same, isn't it? Either you write this as y cap into 1 minus y cap or out into 1 minus y. In our program, we have used the notation, out into 1 minus out. So if you are going to derivate this expression with respect to out or y cap, dou E by dou out, 1 by 2, bring the two term in, reduce the power by 1, and you derivate this component alone with respect to out, because y cap itself out. Okay, this is also equivalent to dou E by dou y cap. Don't get confused with the term. Okay, either you can write in terms of out or in terms of y cap. So 2 cancel, and minus of y cap or minus of out, what do you get? Minus 1. So this expression is minus of y minus y cap So this one is minus of y minus y cap. So one side we have computed this, right? Once we have this, what is our rule? The weight adjustment rule tells that, okay, once you have this guy, all three components, you take a product. Now you can W5 new equivalent to W5 old minus eta times learning rate times. You are going to substitute this whole component over here. Very straightforward. And you will get the updated weight. So that updated weight will try to reduce the overall error function. That is what, because you have provided the gradient, right? This much magnitude, if you change this weight, what is the benefit you are achieving? We are trying to reduce the overall error, right? That is our goal. Parallelly, we are going to see what is happening with the W1, right? This portion is very interesting. This is the place you are going to connect the term backpropagation, the concept of backpropagation. Okay, let us try to write the expression like this here. Let us separate this with a divider. Okay. This one you can easily, you yourself, you can do individually. Dou E by dou W1. I need to compute dou E by dou W1. Shall we break down this equation into two components? Like the way we broke down that expression into three components. Okay, we are trying to break down the expression into three components first. Good morning, Gautam. I'm just recollecting the key points what we have discussed in session 1 and session 2. Okay.
Okay, sir.
Yeah. So you try to write the expression dou E by dou W, and like the way you have done, you multiply and divide by dou out. Since this one you have did at the output layer, so you multiplied and divide by dou out at output layer. But this is out at the hidden layer, right? Your out at hidden layer is nothing but H1. Please understand. This is equivalently, you can write it dou E by dou H1. But I wanted to use a general representation. That's why I use the notation out itself. So multiply and divide by dou out at. Similarly, can you see multiply and divide by dou net? Here net at output, but here net at hidden. Dou net at hidden. The same way I have broke down this term into three components for the easier calculation. So what is the meaning of this? We are going to say how W1 impact net H1, and then you say how net H1 impact based on the net H, your output at the hidden will be impacted, isn't it? So what is this term? Yes, this term is going to say how net H1 is going to impact H1. And finally, how H1 is impacting the error. How H1 is impacting error. So already we know that we have the expression how W5 is impacting the error, right? Now we are going to express how H1 is impacting the error. So again, this term is not directly doable. Again, you have to break down this into three components. What is the meaning of this? Here we have expressed how W5 is impacting the error. W5 is impacting the error. We have taken the indirect route, right? How W5 is impact the net at O. How net at O is impacting the final output, and final output, how it impacts the error. That is why we break down into three components. Now, in the same manner, when I try to break down this into three components, what is our agenda here? I need to say how W1 impact the error. That is the meaning of this error gradient, right? So we are trying to say like, okay, how W1 impact net H1, that is this term, and how net H1 impacts H1, output at the hidden is what? Out H. And finally, you say how output at the hidden is impacting the error. So we break down into three components. So these two terms you can directly substitute. Very simple. Let us see how we calculate these two terms. But for the first term, again, you have to write the chain. Let us work out this. Already we have the expression net at H, right? No doubt, this is the net at H. Net at H, when you derivate with respect to W1, these two terms are constant, right? 0. What you will get? Only X1 you will get, right? When you simplify this guy, what you will get? X1. Like the way derivative of output F dash of net at O, we express that as Y cap into 1 minus Y cap, right? In the same manner, the derivative of the output at the hidden can be expressed as, if I kept this as a H1, I have to express this as a H1 into 1 minus H1, isn't it? H1 into 1 minus H1, like the way Y cap into 1 minus Y cap. So these two terms directly you substitute it. But this one, it's not directly, we cannot calculate, because how out at hidden is nothing but H1. How H1 is impacting the error? Again, you are raising this question. So we have to break down this into three components again. We are going to write dou E by dou out H1. If this term, if it's a bit confusing you, I can also, you can represent the equivalent term. You can shortly refer this as H1 itself. Yeah, output at a hidden is nothing but H hidden, right? So you can write this as H1 itself. Both are same. Output at the hidden is nothing but H1. We represent that as a H1. So you can equivalently write this as a dou H1 in a shorter form. This is what the trick we are going to do. What is the trick? We are going to multiply and divide by the derivative term of out. Even though we calculate this in the hidden side, we are substituting, because anyhow it is not going to impact the original equation. It's going to cancel it out. Net at O, dou net at O. What is the meaning? We are trying to communicate this into three terms. How H1 impacts net O, like the way we write how W5 impacts net O, right? We are writing how H1 impacts net O, that is this term. How net O impacts out, right? How net O impacts out. And we can easily calculate how out impacts E, right? Indirect route, we are taking the same logic. Whatever the logic we applied for W5, we use the same logic. How H1 impacts net O, how net O impacts out, how out impacts E. We broke down into three components and we are going to calculate this. So already we have the net at O expression. This time you are going to derivate with respect to H1. Again, these two terms are 0. What is the value you left out with? W5, isn't it? Now, once again, output at output derivate with respect to net, you will get once again the same term, Y cap into 1 minus Y cap. Okay, because this term is same as this term, Y cap into 1 minus Y cap. Finally, this one, dou E by dou out, which is nothing but this term, right? Same term. It's nothing but minus of y minus y cap. How do you look at this? If you look at this, this is how the backpropagation concept, that is how we coined the term. Because of the mathematics, we are coining the term. Please understand, because of the term, we are not doing the mathematics. Okay. First mathematics is what done. Then only people coin the term. On what is the inspiration to coin the term backpropagation? The inspiration is the mathematics. The mathematics is inspiration. What is the basis for saying backpropagation? While calculating the gradient for W1, please listen this point very carefully. While calculating the gradient for W1, the expression, what is coming to the picture? Whatever the earlier expression is again coming into the picture. Can you see? Minus of y minus y cap into 1 minus y cap term. This term alone, what I told you, you can refer this as a error gradient at the output side. That error gradient at the output side is getting scaled with whom? It's getting scaled with this weight. That means while calculating the gradient for W1, you have this component. Okay, you have this component. What is this component? This is the output side. Sorry. Hidden side error grade. Along with that, while calculating this, what you are getting, this is the delta O scaled by W5. Your output side error gradient is getting scaled by W5. We are getting the component delta naught scaled by W5. It's one of the entity while calculating the output's hidden side error gradient. So you are expressing the hidden side error gradient as a function of your output side error gradient scaled by W5 along with this term. So what is this term? This term is nothing but your hidden side error gradient. So how do you say a minus of y minus y cap times this term? You are calling this as output side error gradient. Now, the hidden side error gradient, how I should call the whole this term, what we call output side error gradient, right? Your output side error gradient. Okay, let me write it in a different place. Okay, this one let me erase this. So this is the final notation. So we calculate the error gradient to adjust W5. We calculate the error gradient to adjust W1. What is the error gradient to adjust W5? We have the notation delta naught. In the delta naught, what are the terms will come into picture? Minus of y minus y cap into y cap into 1 minus y cap. This is the term, right? Similarly, how do you represent error gradient at the hidden side? This term, right? So it's expressed as output side error gradient scaled by W5. So this portion we call is a backpropagated component. Why we use the term backpropagated? Because that is the scaling factor come. If at all that scaling factor should come, means it has to, I have to take delta naught scaled by W5 that is being used to calculate the error gradient at the input side. So that is why the term is being coined like that. Delta naught W5. Along with that, we have this component, right? These two terms. H1 into 1 minus H1, right? This three terms together, what we call error gradient at the hidden layer, right? So final weight adjustment formula, you can write it easily now. How you can write your weight adjustment formula? You can write your first we'll write the formula for to adjust the weight at W5 using delta naught. Okay, W5 new equivalent to W5 initialized, whatever the randomly taken or the previous iteration value, minus learning rate times delta naught. Okay, because I have not included uh, the scaling factor. What is the scaling factor? H1, right? We explicitly we keep this. Without this, the remaining term only we named as delta O, right? So this term. So what is the input to W5? H1 should come as a scaling factor. Similarly, using this delta H, how to update W1? Let me write that expression over here. So W1 new equivalent to W1 old or previous eta times delta hidden, right? The whole term. So the delta hidden comprises of this backpropagated component and f dash of net at the hidden layer. F dash of net at the hidden layer is nothing but H1 into 1 minus H1 times what is the input to this W1? X1, right? X1. Now I'll tell you how you can extend the same gradient value to other model parameters. Okay, you don't need to individually calculate that. Okay, I'll tell you the easy. It is very easy and logically you can easily relate to it. If you trace the network, you can easily connect the same value. Only thing you need to change the inputs. Okay, you have to trace the wiring. If you can trace the wiring, you can easily tell the term for other parameters. Say for example, now I'm going to ask you, hey, tell me how you update a W6. Because I have not drawn the complete drawing. Because you know, your second node is represented as H2, right? And what is the corresponding weight? W6. Now I'm asking, how do you adjust W6? W6 new equivalent to W6 old. The same output side error gradient you are going to use. Okay. Minus eta times delta naught. But what is the only difference? The only difference is you should scale by H2. Here we scale with H1, right? It should be scaled by H2. In the output side, you have only one node, means you get only one value, delta naught. Suppose in the output side, if you have two nodes, assume if it have two nodes, your delta naught also you will have two values. Okay, you will calculate two values. So let us calculate delta naught 1, delta naught 2. I'll show in the program because in our notebook we kept only one node. So your delta naught is a scalar. But as per the PPT architecture, it's given as a two nodes, right? If you have two nodes, you will have two calculations, delta O1 and delta O2. So using delta O1, you have to adjust W5 and W6. Using delta O2, you have to adjust W7 and W8. If you have only one node, means that is a common delta to adjust W5, W6, W7, W8. But accordingly, you have to use the scale factor. Whenever you adjust W5 and W7, H1 is go through W5, H1 is going through W7. So you have to scale with H1. So whenever you adjust W6 and W8 weights, the evenly numbered weights, I should use H2. The odd numbered weights, I should multiply with H2. That alone you have to keep track of the wiring, how the architecture is. So in the same manner, okay, you can easily connect to this side. Okay, this side Okay, let me erase this portion. Now, according to our architecture in the hidden layer, we have two neurons, right? So we have got two neurons. So let us complete the remaining portion of the architecture with a different color so that, okay, let me use a different color. Okay. So the second input, this is X2. This is the second neuron. The output is H2. Like W1, we call this is W2, right? This is W3 and this is W4. This H1 is going here. Similarly, this H2 goes via W6. This part we already completed, right? This is W7 and this is W8 according to our PPT. Now, you tell me you have gradients. When you calculate the gradient over here, you will have two values, H1 as well as your delta H, you will have two values. Okay, here you will have one value, here you have another value. So it's a two-dimensional because you have two neurons. If you have three neurons, you'll get three values. So let us call, if it is like a two neurons, so your delta H dimension will be like a two value. Let us call this a delta H1, delta H2, delta H2. Using delta H1, you need to adjust W1 and W2 can be adjusted using delta H1, including this bias. Including this bias. What is the input to the bias? The scale factor to the bias is 1. So let us call this bias as W bias at hidden 1. We call this bias as W bias at hidden 2. W bias at hidden 1 nu equivalent to W bias at hidden 1 old minus eta times delta H1 times input. What is the input to the bias is 1. Similarly, W1 new equivalent to W1 old minus eta times delta H1 times X1. Okay, this is multiplication. It's not X. It's a multiplication symbol. It's 1, but here it is X1. Similarly, W2 new equivalent to W2 old minus eta times delta hidden 1 times X2. So for X1, X2 and this bias, I should use this value. Similarly, for W3, W4 and this bias, I should use delta H2 and the corresponding inputs. So this calculation we have implemented in the coding. Okay. The only difference is, for simplicity, since we are writing the program without using the built-in package. Okay. Shortly, I'll be introducing the built-in package without using the built-in package. So to reduce the computational workflow, I just keep it one node in the output. For the binary, okay, one hot encoding is optional, but for multi-class, it's mandatory. So I'm going back to the notebook number 2. So another 15-20 minutes we'll be spending on this notebook. Then we'll move on to the real data with the lab 3. So till 12 o'clock maximum, we'll work on this, including the visualization part. Okay, including this visualization part, that is very interesting. With the Plotly Express. Also, I will take you to Professor Skarpathi's JavaScript based visualization. That is also very interesting. So the entire thing will spend another half an hour. 12 o'clock to 1 o'clock. Okay, I will take you to how you can use the library. Number 1, we are going to see the first half an hour. We are going to see 12 to 12:30. We are going to see how to explore sklearn library. And 12:30 to 1, we are going to see how to use a TensorFlow Keras library to solve a problem using a multi-layer perceptron model. So in the forenoon exercise, we are going to concentrate on the regressor problem. Okay, in the afternoon session, in session 4, I will take you to the classification problem. So all the necessary library let us load. We are going to use the sigmodel activation function. That function also defined over here. So we are defining the inputs and weights. This is the weight matrix which connects the input to the hidden, and V vector matrix which connects the hidden to the output. First is the feed forward flow, right? First we are going to see the feed forward flow. First, I'm going to demonstrate stochastic gradient descent. That means I'm going to randomly supply one record and I'm going to calculate the gradients delta naught as well as delta O as well as delta H. Using delta O, we are going to update the output side weight matrix. Here, the output side weight matrix is, who is this output side weight matrix? As per this definition, this V matrix. Using delta O, I'm going to update this guy, and using delta hidden, okay, using delta hidden, we are going to update this guy. That is our agenda. So before calculating this, first of all, I need to supply any one of the training records, and I'm going to calculate the error gradient after supplying the first record. That means what? Record by record error gradient. That means record by record weight update you're going to. What is another style? You supply all the training records, you calculate the total error gradient, and then you update the weight. That is called full batch training. Or you supply first two records, calculate the total error gradient for the first two records, and then update the weight. Then you supply third and fourth record. For that batch, again you calculate the total and then you update the weight. That is called mini batch training. See, these are all the three style of learning. Okay, when we use the APIs with the hyperparameter, we can easily control whether you wanted to apply full batch or mini batch or record by record update. Okay, since it is a handwork demonstration, okay, I'm going to update with the single record I'm going to supply, and I'm going to calculate the gradients. Using that gradient, we'll see how to update these weights. So randomly, I have taken one of the record. Let me see what record I have taken. 10. For 10, what is the target? For 10, the target is 1. Okay. The third record randomly I have taken. So this is randomly initialized weights. With the randomly initialized weights, first I need to supply the data feed forward. The data should navigate the entire architecture and finally it should hit the output. I need to predict y cap and I have to compare that y cap with the actual y. What is the actual y for this? 1. Okay. So if you have to navigate the network, first it has to go through the first phase. What is the first phase? It should go to the weight matrix, W weight matrix. Because W is the weight matrix which connects the input to the hidden. This is the 3 by 3 and your input is 1 by 3. Okay. So 1 by 3 dot product with the 3 by 3, you get a 1 by 3 vector. So first we calculate the net at the hidden layer. Net at hidden layer. So here we are using 3 neurons in this architecture. This is how the architecture looks in this notebook. 3 neurons. Earlier, when we discussed the mathematics, for simplicity, I have taken 2 neurons, H1, H2, but here 3 neurons. But in the PPT, in the output side, I have taken 2 neurons, but here for simplicity, I have taken 1 neuron. So these are all the architectural difference. Doesn't mean whatever the architecture I use, ultimately the end results I'm going to achieve is the final best results I'm going to achieve. There we have only 4 weights, right, in the input to the hidden, W1, W2, W3, W4, while we discuss the mathematics. Here we have, because 3 neurons are there, so I'm going to draw like this. Okay, you can number, maybe you can number this like this. W1, W2, W3, W4, W5, W6. Okay. And also, for every neuron, you have a bias. You have a bias. There is a bias. So, totally 1, 2, 3, 3, 3. 9 weights, right? Those 9 weights are represented by your weight matrix, this weight matrix W. So, this weight matrix is represented as 3 by 3. How 3 by 3? W1, W2, bias. We call this is a bias at hidden neuron 1. So let me call BH1. Okay. Similarly, the second column indicates W3, W4, bias is H2. W5, W6, bias at hidden 3. So that is the meaning of this matrix with respect to the architecture. Okay, if the matrix is given, you should be able to draw the architecture, or if the architecture is given, you should be able to write the matrix. Either way, you should be efficient in doing this. Because mentally you have to visualize this. That this mental visualization will come by practice as you do it over a period of time. This will be helpful in different way when you try to visualize a problem. Okay, when you deal with the tabular data set, how the architecture should be, the raw features should I supply, or if you extracted some features from the images, you should be able to visualize the architecture, how the architecture is. So for that, this exercise will give you that mental picturization. How do you define a problem statement into a architectural, an architectural design? Similarly, for the output side, weight matrix, since for simplicity I've taken only one neuron. Okay. We call this V1, V2, V3, and we are going to call this as a weight at. Okay, this is a weight at the bias at the output side. So we call W suffix VO. So that is why this V matrix is represented as a 4 by 1 vector. V1, V2, V3, V bias at output. So first of all, you should understand the dimension and you should understand the architecture. What is the first step we do? We calculate the net at the hidden layer. So we have got net value. So this is the net value 0.98 we have got here as the output. Actually, it's not output, it is a net value. I have to apply activation function to get the output. Now I apply sigmoidal activation function. Okay, let me apply the sigmoidal activation function. F of net to get the out at. How do we name the out in the PPT? H1, H2, right? The same manner. Okay, this is nothing but H1, H2, H3. Since we have 3 neurons, we have got H1, H2, H3. We have got H1, H2, H3. What is the next calculation? The next calculation, still it is in the feed forward flow, right? Now from the hidden layer, I should transfer the information to the output side. H1 into V1, H2 into V2, H3 into V3 plus W bias O. You get net at output. That net at output, you should pass the activation function to get the final out. We can. So let us navigate this portion. So we calculate what is net at the output side. Okay, because my V matrix is 4 by 1, but whatever the output here I got H1, H2, H3. Okay, with the 3 value, with the 4 value, dot element wise, that is your dot product, it's not possible, right? So what is the scaling factor for V bias 1, right? So I have to concatenate 1 to this result, H1, H2, H3. So that step I have done over here. Okay, I have defined the bias, a scalar. I concatenate to the output. Okay, this hidden layer output I named as y. Okay, you could see that f of net, we named this as a y. Okay, to y, I'm concatenating this bias. After concatenating the bias, I name that variable as y in. Now y in is going as a dot product with the v weight matrix to get the net at the output side. We got net at the output side. Since we have got only one neuron, we got the value as a scalar. Suppose you define two neuron, you have two outputs, like the way how we got three outputs, H1, H2, H3. You may have got two outputs if your output is one hot encoded. Since my output is only one neuron, so you have got only one scalar value. So I'm passing this to the activation function to get y cap. What is y cap? 0.75. Actually, this is the probability score because we have applied to the activation function. But what is the target? 100% probability is the target, right? 1 is the target. But what I achieved, 75%. So I have to improvise the score. I have to bring this probability score close to 1. Then I can, if the probability score increases, naturally your error decreases, because here when you calculate the error, 1 by 2 y minus y cap, 1 minus 0.75 the whole square, 0.25 is very large, right? Similarly, imagine if the probability score is better, like closer to 0.1, say 0.9 means 1 minus 0.9 is only 0.1. So the 0.1 square scaled by 1 by 2, you are minimizing the error in a better way, right? So what is the next calculation? We have successfully traversed our data from input to the hidden to the output. Now the next step is to calculate the error gradients. First step, output side error gradient. You know the formula, output side error gradient. Y minus y cap times y cap into 1 minus y cap. Okay. So in our theoretical formula, we have got the negative sign, but I have taken that negative sign to the weight adjustment. There also one negative sign, that negative, two negatives, I have combined to make it 1 plus. Can you see in the formula, the weight adjustment formula, I'm using the plus symbol, but originally minus. So that minus, and in the gradient, I will get minus of y minus y cap. That minus I combine to make it plus. So, okay, this and all I erase. So what is the calculation now? We are calculating the error gradient, output side error gradient, y minus y cap. Actual y, what is actual y? 1. What is the predicted y cap? Is 0.75. And y cap into 1 minus y cap. This is nothing but f dash of net at the output side. So let me run this. Since we have only one neuron, your error delta dimension is 1, 1 cross 1. If you have two neurons, your error delta dimension will be two values. As I told, delta O1, delta O2, right? But here we have only one delta. So delta O is available. Now it is very straightforward. You can directly update your V matrix. Let us see how to update the V matrix. So before we update the V matrix we kept as a column vector, right? Like a vertical column vector. But your input is arranged as a row vector. So I have to reshape it. Okay, whenever you use this reshape function, minus 1, 1, it will convert a row vector into column vector. But what is the input to V matrix? Output of the hidden. Output of the hidden we already kept as Y in, isn't it? Y in. So you to update V1, V2, V3, okay, to update V1, V2, V3, as of course to VB1, we require these guys. So I need to reshape this to column vector. So that is why I do this. Y in dot reshape, which is converted to the column vector. Using delta O, we are updating the V matrix. So the vectorized representation of this calculation goes like this. If you want to know what is actually happening in this line, it is a vectorized calculation. Let me erase this guy. So this is the initial weight matrix, isn't it? This is the initial weight matrix. So V equal to V plus, that means my initial value, whatever randomly taken value, those randomly taken value 1, 2, 3, 4 values. As per the original formula, we have a minus sign. The gradient minus I have already brought here, plus learning rate times your delta already you computed, which is a scalar 0.0466 into input. Which input is coming to V1, V2, V3? Output of the hidden. The output of the hidden we kept in Y in. We are reshaping to column vector. Again, 1, 2, 3, 4 values. So how the computation will go on? Okay, to get the new V matrix, the first entry, how do you get? This value plus these two are a scalar. These two you multiply and then you multiply with this guy. And you substitute this. Similarly, the second value, you take this fellow plus this product scaled by this. You get the second term, third term, fourth term. So you get the new V matrix. So that is the calculation carried over here. It's a vectorized operation. We have updated the V. Okay. Now it's a very interesting part is a backpropagation. Because to compute the error gradient of the hidden layer, I need to propagate this delta naught via V weight matrix. Okay. Let me erase this. Okay, one important point you should be aware of. Even in the previous session, I towards the end, it's about to close towards the closing this time. I have asked this question. You may not be remembering this. Why we basically truncate this Y in? Y in now we have got, okay, assume H1, H2, H3, and then we appended this one, right? But when you propagate this delta naught, when you propagate, it should go via this. It should go scaled by V2. It should scaled by V3, the back propagation. But we don't propagate in this direction. The reason, this is popular, one of the interview question, or maybe here you consider as a quiz question. The reason is why we don't propagate. What is the purpose and motivation for us to propagate this guy here? To calculate something here, right? To calculate the delta at the hidden. There is no motivation for me to, because it's open-ended. Here we have some wiring. Here there is no wiring. It's open-ended, just the input. Already we updated V1, V2, V3 and V bias. There is nothing is there to propagate the error gradient towards this direction because it's an open-ended network. That's the reason we don't propagate this side. So to scale this delta naught with Y in, what I do in Y in square bracket colon 3. What is this colon 3? The colon 3 is truncating up to this value. And then you scale this fellow. Sorry, not with Y. For this V matrix, we are scaling to colon 3. It's not Y in. V1, V2, V3. So delta naught scaled by V1, delta naught scaled by V2, delta naught scaled by V3. Since we put V of colon 3, we are not propagating in this direction. So these three components. So this one, I'm going to call this as a back propagated component. So let me show you where I have done this calculation. Here, delta O is a scalar value, V colon 3. So delta naught multiply with V1, we got 0.008. Delta naught multiply with V2, we have got 0.0037. Delta naught multiply with V3, we have got this. Okay, this is the back propagated component. So you just at the beginning of our session, we have calculated the formula to compute delta hidden, right? we have this backpropagated component delta naught scaled by V, which is a backpropagated component, along with hidden layer activation. What is hidden layer activation? Output into 1 minus output. The hidden layer output here we kept as Y in, right? The formula is Y in into 1 minus Y in. If you keep it as H means H into 1 minus H. Just the notational difference alone. Y in into 1 minus Y in. So that is why I compute Y in into 1 minus Y in. So that Y in into 1 minus Y in, I have calculated separately over here. You could see here. Y, this is Y, this is 1 minus Y. So Y into 1 minus Y. We keep this component in a variable called Y dash. Okay, I keep this Y into 1 minus Y because I need to product this. Y into 1 minus Y. Again, for this guy, I don't have the one value, right? I don't have the, only Y in will have the concatenated one, right? But I don't require that because you are going to multiply already, that is the vector dimension 3. Here also you should take 3 dimensions. So the fourth one, the bias input is not at all required. So Y into 1 minus Y, this calculation is being done. So again, it's a 3 by 1 vector because I reshaped and showed this as a column vector. Okay, by default, it is a row vector. When I reshape it, it becomes a column vector. So we have to do element-wise multiplication. This is not a matrix multiplication, it's element-wise multiplication. So to obtain this, we have done an element-wise multiplication. Your Y in into 1 minus Y in, you have got 3 entity. And this backpropagated component also, we have got 3 entity, right? It's a 3 by 1 vector. NP dot multiply, what NP dot multiply will do, it's element-wise multiplication. Whereas your dot product will do a matrix multiplication. One should be like a row vector, another is a column vector, sum of products. But this is not a sum of products. It is just an element-wise multiplication. So that your delta hidden, you will have 3 values. So we compute the delta hidden. You have got 3 by 1. Okay. Once you have the delta hidden, what I told you, using first delta hidden, you can control all the weights connecting to the first node, W1, W2, W bias 1. Using this guy, you can control all the weights W3, W4 and this bias. Using the delta H3, you can control W5, W6 and this bias. So whenever you use the first value, I'm going to modify the first column weights. Using this, I'm going to modify the second column weights. Using this, I'm going to modify the third column weights. That step is being done over here. You know, W square bracket colon comma 0, it's going to fetch the first column. While I fetch the first column, look at which delta I have used. Hidden delta square bracket 0. That means the first value, this one I use. Similarly, while fetching the second column, I'm using the hidden delta second value, delta H2. Using the third column, I'm using the square. So your weight matrix got updated with delta hidden value. Okay, let me do this final step over here. Okay, you have got the adjusted weight. So V weight matrix we adjusted, W weight matrix also adjusted using delta O and delta hidden. Now you proceed the same step. Again, present another record, feed forward flow, get delta naught, delta hidden, adjust the weight till the time you reduce the overall error, training error, till the time your data is being successfully classified. You should do this process. Okay. So I just randomly taken one record, and I have navigated what is the feed forward flow and what is the back propagation flow to understand the concept. Okay, now let me clear everything from the screen. We put all together inside a for loop. The whole step, it is included here. Okay, to start with, we start with learning rate 0.01. With initially we start with 1,000 updates. Input V, W, everything is being defined here. Okay, whatever the individual step we have did outside the loop, the same workflow. Randomly we pick a record, we calculate net at hidden, output at hidden, adding the bias, concatenating the bias, net at output, Y cap. At this stage, we compute Y cap. This is the place we got 75% probability for the first third record with the target one, right? And then we computed delta O, Y minus Y cap into Y cap into 1 minus Y cap. Using delta O, we adjusted the weight matrix.